Hello, you absolute legends. My name is Don Cavanaugh, and this is a setup for the lab to identify an unknown weak acid. You're going to identify your unknown weak acid using the molecular weight and the K value for that acid, or K sub A. We're going to go over the setup of the pH electrode, how to calibrate it, a setup and execution of the experiment, and then the analysis of the titration curve and calculations for these two right here. For the setup or calibration of the pH electrode, you have your electrode in distilled water, and you have it plugged in to the Pima laptop. And then you want to open up the program called Logger Pro on the desktop. It'll automatically read that there's a pH meter present right here, and it says pH right here. You want to take your electrode. Now we have pH buffer 7 solution, and it's intentionally dyed green. We want to take a bit of that solution and put our electrode inside of that solution and keep it in there. We're going to keep that solution off to the side while we do the calibration. There's a part up here in the top left-hand corner. Let me pull this in. Experiment, calibrate, this comes up right here. We want to click 1 point calibration. Calibrate now. Enter the value in the data units. We have started with a pH 7.00. Click keep. Hit done. You may have to do this several times during the experiment, but once should be enough as long as you don't shut down the computer. For the experimental setup, the first thing you want to do is weigh out about 0.10 grams of your unknown acid. I'm going to write down exactly how much mass of the unknown acid I used in my notebook. In a clean beaker, I'm going to add my unknown acid that I masked, and then I'm going to dissolve it in distilled water. Doesn't matter how much water I use, as long as it's all dissolved. I might need to crush some of them up, but I can do that. And while I'm crushing them up, I'm also going to add about 3 to 5 drops of the indicator phenolphthalein. Making sure that the acid is all dissolved and that I don't see any more grains inside of the solution. As for the burette, we fill it up with the 0.1 molar sodium hydroxide all the way to the tippy top, 0.00 milliliters. For the setup to be complete, make sure that you have base of known concentration and identity filled all the way up to the tippy top of the burette. You have a known mass of your unknown acid. You have 3 to 5 drops of phenolphthalein. You have enough water, and you have enough water in here to completely dissolve the acid. Doesn't matter how much, just make sure it's enough water. For the setup before you begin the experiment, we have our indicator, our known mass of acid, and enough water in here to dissolve it. We have a base in here filled all the way up to 0.00. We have our calibrated pH electrode. We know there's a weak acid in here, so the pH being less than 7 is all good to go. For the execution of the experiment, please pay attention to this instruction. Simultaneously, one person needs to hit collect, while the other person sets a drip rate of pretty quick pace on this right here. I'm going to try to do that right now. Now, while that's dripping, I'm going to stir it. Okay. And what I'm watching, look at the pink color disappear. Okay. What I'm noting is that as time passes, the pH increases. And I'm looking for the end of the reaction when we are past the equivalence point. We see that it is increasing in pH. I'm getting close to the end of the experiment. I'm going to wait for this line on my laptop to flatten out, and then I'm going to simultaneously hit stop and close the nozzle at the same time. It's starting to flatten out, but I'm just going to make sure, wait a few more seconds. It's definitely starting to flatten out. All right, so the experiment, I've completed it. I ended it when it started to flatten out, and I simultaneously hit those numbers there. When the experiment is over, we want to note the time that has elapsed, and we want to see the total volume of base that was dispensed to calculate the drip rate. Since you started your burette at 0. This was the total amount of base dispensed. This is the total time. So this is our drip rate in milliliters per second. The reason why we need the drip rate is because our x-axis is in seconds, not in milliliters. After finding the drip rate, I want to find the steepest part of this curve. To find the steepest part of this curve, or the equivalence point, I can use my cursor here to get a guess that it's around 50 seconds. Coming back up in here, I want to look at two data points that have the greatest change in pH over these 2-second intervals. So after looking over these numbers here closely, this appears to be the greatest change in pH between any two data points. So that means at 47 seconds, we had the greatest change in pH. At 47 seconds, we had the greatest change in pH, and that represents the equivalence point. That means that the half equivalence point occurred at 23.5 seconds. For the equivalence point, I need to know the moles of base that has been dispersed. So at 47 seconds, this is where the drip rate comes into play. At 47 seconds, with a drip rate of 0.205 milliliters, that doesn't work. 0.205 milliliters per second. That'll give me the milliliters that has been dispersed. Now that solves for liters that has been dispersed. And the molarity, finally, it was 0.1 moles per liter was the solution. At the equivalence point, 0.00096 moles of base must have been dispersed. Because this is a 1-to-1 balanced chemical reaction, we know magically or immediately that the moles of base, now we immediately know the moles of acid that are present. At the half equivalence point, we want to know the pH at this time, 23.5 seconds. Let's go back to the screen. Back to our computer screen here, the half equivalence point was determined to be at 23.5 seconds. So between 22 right there. So it's somewhere in between 5.39 and 5.51. I am going to say that that is 5.45 pH, pretty much right in between there. 5.45 pH is the half equivalence point. Now at the half equivalence point, the ratios of the base and the conjugate acid are equal to each other. So at the half equivalence point, the pH is precisely equal to the pKa. The pKa of the weak acid is 5.45. No units on that because it's a pKa. This is Googleable on Wikipedia. The molecular weight of the acid. The molecular weight of anything is grams over moles. I know the moles of acid, and I know the grams of acid because I weighed it out on the scale there. So the molecular weight of the acid is 0.12 grams divided by 0.00096 moles. That was calculated. So I have a molecular weight of around 125 grams per mole, and I have a pKa value of 5.45. In the lab, you're given 3 to 4 usual suspects to investigate the Wikipedia pages to try to determine what is your unknown. I hope this helps. Thank you.